9B temperature, 9.6 thermometric properties. You may feel hot on a steamy summer day or cold on a snowy, blustery day. These descriptions are subjective, which means that they depend on how you perceive hot and cold. However, they are scientifically useless. Scientists need an objective standard for measuring temperature, not one dependent on uncalibrated human perception. The temperature of a substance is directly related to the average kinetic energy of its atoms and molecules. It is measured in a dimensional unit called the degree. The change of hotness per degree varies depending on the temperature scale, Fahrenheit, Celsius, or Kelvin. We measure temperature with an instrument called a thermometer. Thermometers work by exploiting a thermometric property, which is a physical property of matter that changes predictably with a given change of temperature. Most thermometers you're familiar with depend on the thermal expansion of liquids or metals, or on the change of an electrical property to detect temperature. Most thermometers work through direct contact with the substance whose temperature they are measuring. If the substance is warmer than the thermometer, thermal energy is transferred from the substance to the thermometric material. As the thermal energy of the thermometer's particles increases, it indicates a higher temperature. If the substance is colder than the thermometer, it removes thermal energy from the thermometric material, and the thermometer indicates a colder temperature. 9.7 Early Thermometers. One of the first thermometers was built around 1600 by Galileo. The thermoscope, as Galileo called it, consisted of a long, slender glass tube with a sealed bulb at one end. It was inverted with its open end in a flask of water. The level of water in the tube rose and fell as the volume of air trapped inside fluctuated with its temperature. Later scientists revised Galileo's design by replacing the air, which was the thermometric substance, with a combination of alcohol and water in a sealed tube. Sealing the tube eliminated the effect of atmospheric pressure on the temperature reading. 9.8 Temperature scales. A serious challenge for early scientists was the marking of their thermometers' scales. They needed to calibrate them so that the instruments reliably indicated the correct temperature. For scientists everywhere to obtain the same readings with their thermometers, they needed to agree on the anchor or standard points for a temperature scale. These needed to be fixed, precisely known, and easily reproducible temperature values. Such standards for a measuring scale are called fiducial points. The Fahrenheit scale. In 1714, Gabriel Fahrenheit tackled the problem of developing a reliable thermometer. He preferred mercury to the alcohol-water mixture because it could be used for higher temperatures where alcohol would readily evaporate. He initially selected two temperatures as fiducial points for his thermometer: the freezing point of a mixture of salt, water, and ice, and the temperature of the blood of a healthy man. After some further experimenting, he settled on a temperature scale with the fiducial points at the freezing and boiling temperatures of pure water. On the Fahrenheit scale, there are 180 degrees between water's freezing point, 32 degrees Fahrenheit, and boiling point, 212 degrees Fahrenheit. The design of modern liquid thermometers is essentially the same as Fahrenheit's original. The Celsius scale. In 1742, Anders Celsius devised a decimal temperature scale. The temperature range between the freezing and boiling points of water was 100 degrees. He also extended his scale above and below the fiducial temperatures. Interestingly, Celsius placed 0 degrees at the boiling point of water and 100 degrees at the freezing point, just the opposite of the standard arrangement today. In 1744, the scale was switched after Celsius's death, so that values interraced with temperature. Because of its convenience and decimal basis, the Celsius scale was adopted by the French Commission that designed the metric system. Most countries and schools and almost all scientific laboratories currently use the Celsius scale. You may have noticed that there are fewer Celsius degrees between the freezing and boiling points of water than Fahrenheit degrees, 100 versus 180. Thus, a Celsius degree is larger than a Fahrenheit degree. In addition, the scale values for the Fahrenheit and Celsius fiducial points differ. These differences make relating temperatures between the two scales inconvenient at best. Though most of the world uses the Celsius scale, the United States still depends on the Fahrenheit scale for most familiar purposes. Sometimes conversion between these scales is necessary. Probably the easiest way to convert from one temperature scale to another is to use an internet conversion service or an application downloaded to your computer, tablet, or smartphone. In many web browsers, just typing a phrase like "convert 72 degrees Fahrenheit to Celsius" in the search field will yield the equivalent Celsius temperature. For classroom work, you can use two formulas for this purpose. The most familiar one converts the Celsius temperature to Fahrenheit degrees, using the conversion factor 1.8 degrees Fahrenheit per degree Celsius, and then adding 32 degrees to reference the temperature to the Fahrenheit value of water's freezing point. TF equals 1.8 Tc plus 32 degrees, where TF is the required Fahrenheit temperature and Tc is the given or known Celsius temperature. The second and possibly less familiar method is probably easier to remember for when you are converting temperatures while stranded on a desert island. It works because the temperature minus 40 degrees is the same temperature on both the Fahrenheit and Celsius scales. It uses the same conversion factor for Celsius to Fahrenheit degrees, 1.8 degrees Fahrenheit per degree Celsius. TF, share 1.8, Tc plus 40 degrees minus 40 degrees. If you wish to convert from Fahrenheit to Celsius, just solve either formula for the Celsius temperature using simple algebra. The new conversion factor is the reciprocal value of the original, that is, 1 degree Celsius per 1.8 degrees Fahrenheit, or 5/9 degrees Celsius per degree Fahrenheit. The new formula is Tc equals 5/9 times Tf minus 32 degrees. If you are using the second method, the only thing you will have to change is the conversion factor, which is Tc equals, open parenthesis, 5/9, close parenthesis, Tf plus 40 degrees minus 40 degrees. The Kelvin scale. Scientists in the early 1800s discovered that gases had interesting properties at very low temperatures, far below the freezing point of water. Studies based on Charles's law indicated that if gases were cooled to a sufficiently low temperature, gas pressure would disappear. The Celsius temperature for this point was calculated to be about minus 273 degrees Celsius. Scientists found that devising mathematical gas laws that worked at all temperatures was difficult because of the negative temperature values. Lord Kelvin recognized that temperature is related to thermal energy content. He suggested that the temperature of matter in which no more thermal energy can be removed is the coldest temperature possible. In 1848, Kelvin proposed a temperature scale in which this temperature was assigned a value of 0, also called absolute zero. All higher temperatures were positive values. The degree in Kelvin's scale is equal to the Celsius degree in size. On the Kelvin scale, the freezing point of water is 273.15 Kelvin. For the Fahrenheit and Celsius scales, two fiducial temperatures were used to anchor the scale. What points could be used for the Kelvin or absolute scale? Absolute zero is unattainable according to the laws of thermodynamics, so it could not be a measurable fiducial point. After considering this problem, scientists decided to use only one fiducial point, the triple point of water. A substance's triple point is the temperature and pressure at which solid, liquid, and gaseous phases of the substance simultaneously exist in a stable condition. Water's triple point is 0.01 degrees Celsius and 611.73 pascals. On the Kelvin scale, the triple point of water is 273.16 Kelvin. Scientists then defined 1 Kelvin as 1 over 273.16, the triple point temperature of water. Conversions between Kelvin and Celsius temperatures are easy to do. Since the Celsius degree and the Kelvin are the same size, it is simply a matter of adding or subtracting 273.15 degrees as appropriate. To convert Celsius to Kelvin, add 273.15 degrees. T equals TCE plus 273.15 degrees. To convert Kelvin to Celsius, subtract 273.15 degrees. Tc equals T minus 273.15 degrees. 9.9 Matter and temperature. Temperature can have significant effects on important properties of matter. Engineers design products to take advantage of these temperature-dependent properties. or try to avoid the problems they cause. This section covers a few of the important properties of matter that are affected by temperature. Thermal expansion. The center span of the Verrazano Narrows Bridge in New York City soars 66 meters, 216 feet, above the water at its middle, but only on a cold winter day. The bridge and its suspension cables lengthen as they grow warmer. On a hot summer day, the concrete and steel span droops 3.7 meters, 12 feet. Most materials have the property of thermal expansion. Bridge designers must leave gaps, called finger joints, between sections of the road surface so that the bridge can expand without buckling. Long bridges also have rollers at support points so that expansion and contraction will not damage the bridge foundations. Roads and sidewalks are built with compressible strips between the concrete slabs to allow the concrete to expand and contract with temperature changes. Thermal expansion occurs at the particle level, where greater thermal vibrations at higher temperatures force particles farther apart. If an object is long and thin, like a wire, the expansion is most noticeable along its length. The increase in length is directly proportional to the number of particles lined up in a given direction. A long, thin object expands much farther along its length because it has many more particles lined up in that direction than it has across its width. 1% of a length of 200 meters is a greater value than 1% of a diameter of 1 centimeter, 0.01 centimeters. For this reason, high-voltage transmission wires suspended between electrical towers can sag a meter or more in summer, but the change in their diameters is hardly noticeable. Every material has its own unique thermal expansion properties. For example, for the same temperature increase, brass expands almost 7 times as much as porcelain. The solid and liquid phases of most substances expand at about the same rate for a given temperature change, because their particles remain relatively close together. The gas phases, however, show a much greater volume change per degree change in temperature. Electrical resistance. Certain materials that are excellent thermal conductors, such as metals, also conduct electricity well. One way to measure a material's ability to conduct electricity is to measure its electrical resistance. The greater its resistance, the poorer its conducting ability. See Chapter 10 for a more complete discussion of electrical resistance. When the temperature of a substance increases, its electrons, which are involved in bonding atoms together, move more chaotically. They no longer flow easily in one direction, which is essential for carrying electrical current. The material becomes more resistant to the flow of electrical current as its temperature rises. Electrical transmission wires heated by the sun are a problem for electric companies because it takes more energy at the source to send electrical current through the higher electrical resistance. Viscosity. Another material property strongly affected by temperature is viscosity, a fluid's resistance to flow. Liquids like rubbing alcohol have low viscosities. Liquids like thick corn syrup and certain oil treatments are highly viscous. Viscosity generally decreases in warmer fluids. It decreases because the molecules vibrate faster and move farther apart so that they have less attraction for one another. Less viscous liquids are easier to pump, so engineers often try to warm liquids in piping distribution systems. On the other hand, lubricants depend on at least some viscosity to coat surfaces. Motor oil is used to lubricate car and truck engines, but if the oil gets too hot, it loses its viscosity and is less effective at reducing friction between moving metal parts.